Hi, and welcome back. Today we're going to look at how you estimate variance when you have historical data or just observations. So, last time we looked at how to compute the variance and the standard deviation, and then we used this formula where Pj stood for the probability of event j, xj was the outcome in case event j happened, and e of x was the expected value of x. If you put it on this form instead, we could say that x1 was the outcome if event 1 does happen. P1 was the probability that event 1 does indeed happen. And e of x was the expected value. So within the parentheses, this was the deviation from the expected value in case of event 1. So how much do we get if event 1 happens compared to what the expectation is? When we did the variance of a card game, and then you multiplied the probability of a 7 being drawn, which was 1 divided by 13, times within the parentheses then, the outcome in case a 7 is drawn, which was 2000, minus the expected value of 61.54. So you had a deviation from the expectation in case we had a 7. And then we square this by 2 to make all deviations positive. Then we add the probability of event 2, which is drawing some other card than a 7, which is 12 divided by 13, times the outcome of drawing some other card, which was then minus 100, minus the expectation of 61.54, and then again we squared it by 2. We found this to be 313,136.1, and this was in some strange unit called squared kronor or something like that. The student who are very who's observant might see that I've changed the probabilities in this video from the last one. So now I have 1 divided by 13 and 12 divided by 13 instead of last time I had 4 divided by 52 and 48 divided by 52. This is the same number actually, and the reason is of course for example, hearts, you have 13 cards. Of those, one is a 7 and the other cards are 12. So in all different colors of the card, you have one out of 13 that it is a 7. So it's the same numbers. And again, this P and X and just denote that if we have more events, we should consider those as well. Okay, but let's say that we look at some how the stock market has gone from the years 2008 to 2012. Then we can see that in 2008 we had a very bad year of minus 50%. 2009 was a fairly good year, plus 32%. 2010 was fairly good, and so on. But if we want to use that formula before, then we need the probabilities of these events actually happening. And we can't say that. I mean, we can observe that it did happen, but it's not the same thing as knowing what the actual probability that it would happen was. If you draw a 7 from a card, from a deck of cards, then you know that it's a 1 divided by 13 chance that you get a 7. But if you only have like observations that, well, they drew a 7 and then they draw a 7 again, and they draw a 7 again, and they draw a 7 again, you might think that the probability of drawing a 7 is very high, even though it might all just have been due to chance. And the same here, we have no idea what the actual probabilities were. We just know that these returns actually did happen. So we can't use the same formula, and we need something else. So instead of expected return, where we also needed the probabilities, we're going to use what is called the arithmetic average. And that's just the normal average that you think of. You add up all numbers, all observations, and then you divide it by the number of observations. So we denote it by x bar. So this thingy above is called bar. And we call that arithmetic average. N stands for the number of observations. Xj stands for the outcome in period j. So the summation says that we should sum all outcomes and then divide it by n, like the number of observations. So to do it then, you would simply do it like this. You take the return in the first year, which then corresponds to x1, and you write it here. Then you add the return in the second year, which was 32.53%. You add the outcome in the third year, so now we go here to the 3 dots. We add the outcome in the fourth year, again, it's contained within those dots. And now in the fifth year, that would correspond to our last observation, so that would be xn. Add that, and then you divide it by the number of observations, which is in this case 5, because we have 5 years. And we find that the arithmetic average was 2.91%. So that would be our expected outcome. Okay, sometimes when you look at a time series like this is because we have data from 2008, 2009 and so, you use a slightly different notation. So for example, we use a big capital T instead of the N that we used earlier. It means the same thing, it's still only the number of observations, but in this case it would mean maybe the large T would be the last year that we have here. Also, we have changed the X to R's, so before X was a random variable, now it's more obvious that we're talking about returns, because in this case we actually have returns. And finally, we changed the small index from J to T. And again, the reason for this is that we're talking about a time period. So x1 here would mean the outcome in the first year, the outcome in the second year, and so on. And this would be the outcome in the last year in our observations. So it's still the same formula, nothing has changed, we're just using slightly different notation. Okay, another thing on different notations, when we talked about expected value, we said that we could use either e of x or also the Greek letter mu. And now in the next slide I will use mu only because it takes less space. Otherwise it would be very hard to read on the screen. So when you estimate variance using historical data, we cannot use this formula. So first of all, we don't have any probabilities. Second of all, we don't have an actual expected value. We have this arithmetic average, which we use instead as an expected value. So the formula is going to change slightly, and it's going to change in this way. First of all, we replace all expected values by this arithmetic average, which is our estimation of the expected value. Then we ignore all the probabilities because we don't know the probability of the outcomes that actually happened. Instead, we're going to divide it by n minus 1. And why divide it by n minus 1 and not by n? It's a fairly technical thing which I'll leave for your statistical courses later. But that's how you do it anyway, usually. Okay, so let's actually do this example and then calculate or estimate the variance. So, sorry, I prepared an Excel slide. Let's see if I can zoom in a little bit. Okay, so here we have the returns, the same as in the slides. We have the average return here, and we want to compute the variance and the standard deviation. So remember now, we are supposed to take the outcome in the first year minus the arithmetic average, and then we're going to square it. So this column here, that's going to be filled by these squared deviations. So we want to take x1 minus the arithmetic average. So we do it here, we write equal to, we take x1, the outcome in year 1, minus the average return, or the arithmetic average. Okay, so that's the first part. Then we're also supposed to write this within parentheses and square it. So we take this within parentheses and we square it. And then one last thing I'm going to do, I'm going to add dollar signs in front of f and in front of the 10. This means that I lock the cell which is the average return, because all of these want to use the same average return. Because now Excel is fairly smart. If I click enter here, sorry, I have a small black box here in the corner, and if I click here and hold, I can drag down. And what will happen then is that Excel will automatically update the formulas so that they refer to the return in the second year minus the arithmetic average. They refer to the, in this case, fourth year minus the arithmetic average. So I have all of these are computed by Excel, and I don't have to type it in anymore. The only thing I had to do was to lock in the arithmetic average, because that one is used by all different years. Otherwise, I wanted it to jump down. Okay, so now we have all these individual ones, and we are supposed to sum them. So we can do that by writing equal to, and take this one plus that one plus that one plus that one plus that one. Or, of course, we could use the formula sum, or well, I have a Swedish one, so it's called summa. In English, it would be sum. And we simply select these cells, H4 to H8, so we use this column then to get all of them. And then we get the same number, of course. Finally, so now we've taken the individual square deviations, we added them, and to get the variance, we need to divide it by n minus 1. So to compute the variance, we take this one and we divide it by 5, which is the number of years, minus 1. So our estimation of the variance is 0.3035. Standard deviation, as you remember, is the squared root of the variance. And if you don't know what the formula for square root is, you can always take it to the power of 0.5, or you can actually write it like 1/2. So taking it to the power of 1 divided by 2 is the same thing as taking the square root. Okay, and we find that the standard deviation is 36.5%. So we might want to write this as percentage and add some decimal. So 36.53% is the standard deviation. Okay, so let's go back here. Variance and standard deviation, again, measures the same thing. The variance is expressed in strange units, such as squared kroner or squared percentage in our case. And the standard deviation then is a measure of how big a normal or a standard deviation is from the expected value, and is always expressed in the same unit as the outcomes that we have in our case. So in the last example we had percentage return. It means that the standard deviation was also expressed in percent. Okay, that's it for today. Thank you very much.